Hi, my name is Abhishek from Institute of Aeronautical Engineering. My roll number is 209518210. I am from Aeronautical Engineering branch. Today I want to discuss about Gaussian elimination method. In mathematics, Gaussian elimination, also known as row reduction, is an algorithm for solving systems of linear equations. It consists of a sequence of operations performed on the corresponding matrix of coefficients. This method can also be used to compute the rank of a matrix, the determinant of a square matrix, and the inverse of an invertible matrix. This method is named after Carl Friedrich Gauss. Although some special cases of this method, albeit presented without proof, were known to Chinese mathematicians as early as circa 179 CE. To perform row reduction on a matrix, one uses a sequence of elementary row operations to modify the matrix until the lower left hand corner of the matrix is filled with zeros. As much as possible, there are three types of elementary row operations: swapping of two rows, multiplying a row by non-zero number, adding a multiple of one row to another row. Using these operations, a matrix can always be transformed into an upper triangular matrix. And in fact, one that is in row column form once all of the leading coefficients are 1 and every column containing a lead coefficient has 0 elsewhere. The matrix is said to be in reduced row echelon form. This final form is unique. In other words, it is independent of the sequence of row operations used. For example, in the following sequence of row operations, the third and fourth matrices are the ones in row echelon form, and the final matrix is the unique reduced row echelon form. See, C1, C111, C11, C12 form up to N, and when we are taking this using row operations to convert it into reduced row echelon form is sometimes called Gauss-Jordan elimination. While we are eliminating one column, the term Gaussian elimination refers to the process until it has reached its upper triangular or unreduced row echelon form. For computational reasons, when solving system of linear equations, it is sometimes preferable to stop row operations before the matrix is completely reduced. Definitions and example of algorithm. The process of row reduction makes use of elementary row operations and can be divided into two parts. The first part, sometimes called forward elimination, reduces a given system to row echelon form, from which one can tell whether there are no solutions, a unique solution, or infinity many solutions. The second part, sometimes called back substitution, continues to use row operations until the solution is found. In other words, it puts the matrix into reduced row echelon form. Another point of view which turns out to be very useful to analyze the algorithm is that row reduction produces a matrix decomposition of the original matrix. The elementary row operations may be used as the multiplication of the left of the original matrix by elementary matrices. Alternatively, a sequence of elementary operations that raises single row may be used as multiplication by Frobenius matrix. Row operations. There are three types of elementary row operations which may be performed on the rows of a matrix. While doing Gauss elimination method, we must know the row operations: multiply by row by non-zero scalar, swap the positions of the two rows, add to one row a scalar multiple of another. The matrix is associated to a system of linear equations, then these operations do not change the solution set. Therefore, if one's goal is to solve a system of linear equations, then using these row operations could make the problem easier. Echelon form. For each row in a matrix, if the row does not consist of only zeros, then that leftmost non-zero entry is called the leading coefficients of that row. So if two leading coefficients are in the same column, then a row operation of type 3 could be used to make one of those coefficients 0. Then by using the row swapping operation, one can always order the rows so that for every non-zero row, the leading coefficient is to the right of the leading coefficient of the row above. If this is in the case, then matrix is said to be row echelon form. For example, the following matrix is row and it leads to coefficients x plus 5 plus z equal to 2, 6x minus 4y plus 5z equal to 31, 5x plus 2y plus 2z equal to 13. Augment matrix for the above three reactions will be for x coefficient 1, y 1, z 1 from last 2, 6 minus 4, 5, 31, 5, 2, 2, 13. As we know, and by seeing this we can easily understand. Row echelon form. A matrix is in row echelon form if all rows with at least one non-zero element are above all zero rows. The first non-zero number from the left of a non-zero row is at the right of the leading coefficients of the row above it. For example, by seeing this matrix, we can the system of equations x plus 5 plus z equal to 3, 3 to x plus as argument matrix, while we are taking the question x equal to 1, 1, 1, y1, z1, 3 and 2, 3, 7. Row operations can be used to express the matrix in row echelon form. Means we have to divide the portion and make the echelon form. Why we are making echelon form? This upper triangle matrix, the triangular matrix will make, and the solutions are 1, 4, 2. It's minus 2. As you know, we are understanding this. Gauss elimination method makes us to divide, and thank you for giving this opportunity.